Okay, it looks like we're live, and I can see the YouTube chat, and I can see one watching is probably me, but that's great. We are going to go through some of my Zotero backlog. So let me just actually clear this so you can see the scope of the problem. Lots and lots of. Okay, it looks like we're live. Need to mute the stream there. Yeah, lots and lots of tabs, lots of open papers that I want to go through. So hopefully you'll come along for the ride, and this will be a nice, slow, gentle, long stream. I just want to read through these papers, attempt to explain both my process as I'm approaching them and my best understanding once we've had a look at them. We're not going to go in depth on all of these because there's a lot to get through, but I do want to work through them, keep a few for later, but just close off most of them as, these are all things I've been intending to look at or have seen referenced by someone and popped in. So this is just clearing that backlog. If you see things that you want to know more about, and I'll reiterate this a few times as people join, please put questions in the chat. Put questions, put thoughts, put comments, and that'll help steer what we spend lots of time on and what we kind of skim over. And if you have, additional paper suggestions, I'm open to that, but as you've seen, we've got quite a few to get through. But yeah, with that being said, I'm going to start, and then I will periodically re-intro if I see people joining. But so far, I don't think we've got anyone watching, so I'm going to get a head start. Okay, so this is one that I opened a fair bit ago. Reinforcement learning for reasoning in small LLMs, what works and what doesn't. And there's a whole flurry, right? After DeepSeek published their R1 paper, and a few other similar papers came out at the same time, the Kimi 1.5, also using reinforcement learning from verifiable rewards, and the actual paper called RLVR. There was this huge explosion of applying that same type of recipe reasoning on questions with known answers to big models, small models for a million different tasks. And as we'll see, not all of them were equally rigorous. So I opened up a few. We'll take a look. This one I actually haven't read, but this is one of many in this genre of taking some of these recipes and trying to adapt them for smaller models or for different tasks. And so that's probably a theme that we'll see going through. Okay, so we want to enhance the reasoning capabilities, and reasoning here used often just to mean this kind of thinking via chain of thought, producing lots of thinking tokens before you produce your final answer, using reinforcement learning to improve the final accuracy on specific tasks, in this case something like mathematics, competition mathematics. So they say we're going to have something that's focused on a much smaller model than the DeepSeek R1 paper. Strict constraints, training on 4 GPUs for 24 hours. So a nice constrained, small, this is something you could approach as a small research lab, maybe even as an individual, versus the, we dedicated a giant cluster for several months to train. And they show rapid gains, at least, yeah, that's the claim, that this is going to be, at a $40 training cost, they're getting a huge improvement for these small things, and they find some challenges as well. So I'm really curious approaching this paper, just what are the techniques that are emerging from this kind of flurry of people attempting to do this? What are the pitfalls? What works, what doesn't, exactly what they say in the title, what works and what doesn't. So I'm keen to take a look. We'll probably just spend a little bit of time seeing if they have key highlights. Okay, so lots of different attempts to do reasoning. Small models present a good deployment option, but it takes a while to train reasoning models. So we want to ask, how do they do with strict constraints, and can you boost them with RL? And so here's the sort of flagship figure, their model in red, getting much higher pass, accuracy on these evaluations, for a much lower training cost and a much smaller model size versus a number of others that they're comparing to. So we're going to be asking, how are they doing this? Does this seem like a legit result? And what are the tricks? So they're analyzing the reasoning potential of small models, they're giving actionable insights, and they have source code and data sets. That's fantastic. Okay, so what is the trick? Step 1, high quality data curation. Fantastic. So they have an existing data set that is 60,000 questions, focused on math and including problems for the AIME, which is Mathematics Olympiad, and that's what they're going to be evaluating on. But this is 1983 to 21, and the eval is 2024. So seems good. Deep scale R, another data set, more math, more OmniMath, and still focusing on mathematics, and they're combining those two. Okay, then the RL is using GRPO, so that's the same as DeepSeek. If someone has a question about that, we can look at that, but I think that's beyond the scope for this paper. But the idea is that we're going to produce a bunch of completions for every given input, right? So I get one math question, I produce, say, 4 or 8 or 16 answers. I'm going to evaluate whether those answers are correct, and then assign some reward. So maybe correct answers get a 1, everything else gets a 0, or there's some sort of degrees of correctness for some problems, you know, like how many stages in the proof are correct or something. And then we'll take the rewards for the whole group, and we'll kind of average them and use that as our feedback signal. So there's no dedicated value model. We're just using those calculated rewards on those group of different completions for the same input. And so we are trying to make it so that our advantageous ones are more likely with our new policy, and our less advantageous ones are less likely with our new policy. So you can imagine, you know, if I scale my rewards, so some of them are like plus 0.5 and some of them are minus 0.5, right? Then for the ones that have a positive reward, that say the first completion is good, I want to make that more likely under my currently training policy. For the ones that are bad, I want to make them less likely, but I do some clipping so I'm not making too large of an adjustment, and I also have a KL divergence term to stop me drifting too far away from the reference policy. Now, some papers I've seen discard this KL term or use a very low beta, so I'll be interested to see what they do here. And like I said, this advantage is from a group of rewards, just normalizing those rewards based on the group. Okay, so reward models, they have a rule-based system, that's great. Is the model response correct? Scaling it based on response lengths, so in other words, penalizing ultra-long reasoning. That's an interesting choice, but pretty good, because otherwise the response length tends to grow through training more and more, and that gives you less efficient training. And then a format reward just to get it, especially in the beginning, following the kind of formatting that you want. Fantastic. Okay, so we've got our setup. We've got, seems like pretty vanilla GRPO. We've got some math questions for training. We have a way of assigning our reward and updating our model. So how do we do this RL for small models? That's the question that we're looking to answer. They've got some benchmarks. They're going to compare their model against a bunch of others. Okay, so what are the actual experiments here? Trying 3 experiments. Okay, impact of high quality data. So using this data set, and the performance improves a little bit on math and a lot more on AI or AMC23, which is another math type exam. Okay, so far that seems to be like, oh, we ran the training and it got better at math when we trained it on a bunch of math using RL. That seems expected. But I guess that gives us this insight. Small LLMs can achieve rapid reasoning improvements, but if you're training for a long time with the length constraints, apparently your performance degrades again. Okay, so I guess this is what they're talking about. You get an increase and then a decrease. Yeah, I don't know that I'd necessarily strongly interpret it like that. This could be that we're training on something more like this domain and less like this domain, right? And so a little bit of training in any kind of math skews it from general model to math model, and that gives us improvements across the board. Then as we hyper-focus on Math Olympiad style exams, maybe our performance on math, which is slightly different, it's very, very similar, but still I could see that dropping a little bit. I don't know, it also looks very noisy, but we can see at least some improvement pretty quickly, relatively small number of training steps using this RL approach. Okay, lots of people have found that. Experiment 2, balancing easy and hard problems. And this is something some of the bigger players have done as well, is carefully selecting questions where within your group of completions, you don't get them all right, which would indicate a question that's too easy, and you don't get them all wrong, which would indicate a question that's too hard. So they draw some samples. I don't see exactly how they're choosing the easy versus hard. And They say a mix of these two enhances performance and stabilizes reasoning. I'm not seeing a ton of detail. I might skim the rest of this. Okay, controlling length of cosine stabilizes completion lengths, but extending length for hard tasks is necessary. Okay, so far this is all pretty common sense stuff. And they end up with a model that's presumably pretty good. Okay, so actually really small paper, maybe not so with studying ultra deep. And kind of related to that, this is one that I have looked at before and that captures a lot of what's going on in many of these papers. A sober look at progress in language model reasoning, pitfalls and paths to reproducibility. This is the next frontier, everyone's working on this, but there's often a lack of methodological rigor. Apologies to the previous paper, I'm not reading this right after you just to say that that one in particular is at all bad, but in general this whole space seems like it's full of potential for issues. So these guys look at a bunch of the mathematical reasoning benchmarks and approaches and find that they're highly sensitive to subtle choices, like how exactly you do the evaluation, what seeds, what prompt formatting, because we're working with, each of these exams only has quite a small number of questions. They're often only run once, and so you saw in the previous one, there was this very noisy graphs of accuracy over training. These guys find that basically there's a lot of noise in this process and a lot of subtlety, and so for a lot of these different small open reasoning models that have shown really good results, when this paper tries to replicate those results, they often see quite a drop in accuracy, either just because they happen to pick a less good seed or some other slight difference between the two accounts for a large drop in performance. So I thought that was a good sobering look. The same thing happened with anything that's like computationally approachable, right? So you're trying to get your papers ready for your PhD or whatever, trying to get into some conference. You're saying, well, I can't pre-train a giant model, right? I'm not OpenAI. I don't have millions of dollars and thousands of GPUs. What can I do? And so, like, for example, when LoRa came out, this really great idea, low rank adaptation for fine-tuning efficiently. There's a million different variants of LoRa, right? And some of those were like genuine, really good improvements, like Dora. But a number of them were more like, oh, we did this slightly different initialization or the slightly different training, or we did it on different layers. They train on some arbitrary data set, they show some improvement on some arbitrary benchmark, and then they get published. And often that's somewhat valuable, especially for learning for those authors, but it's also a lot of noise. And I feel like the same thing is happening now with reasoning. Great, there's these big headline things, everyone's talking about DeepSeek. We implement GRPO, we train some small model on some small data set, we see some improvement on like math or GSM-8K or whatever, we write it up, we publish it, but a lot of that's actually not going to necessarily translate across problems. It might just be you got lucky, or that even fine-tuning on your data set would also have gotten a boost. So yeah, this is a good cautionary tale. They go into like how they did the evaluations and stuff. So I'm a fan of keeping our expectations tempered. I love small experiments that anyone can do, right? Like I'm a big fan of that. I just think this is a good call to maybe be a little bit more rigorous, to run multiple runs, right? If you're trying to report your accuracy on some evaluation data set that only has 50 questions or whatever the small number is, run it a number of times, use bootstrapping to estimate your uncertainty bounds on your report to see whether you actually have an improvement or you just got lucky. This has bitten me before, right? The small scale test on 50 samples looks really good, but you just got lucky with the questions, and when you rerun it on 500 samples or 1,000 samples or multiple times, varying the temperature, you find that actually your improvement goes away. Okay, I'm going to take a small pause to see if there's anybody watching. Hey, we do have a couple of people watching. Welcome. Thank you for joining. If you've just joined, this is a very chilled, casual stream to work through a number of papers that I've been meaning to look at and then close them off. So thank you for coming, and we're going to keep working through those now. Oh, and please say hello in the chat, so I can see that there's some people watching. Okay, retool reinforcement learning for strategic tool use from ByteDance. Okay, so this is another sort of sub-theme within the general RL on small LLMs, teaching them to use tools. So latest models like O3, they don't just produce these kind of thinking tokens, they also incorporate things like search, like zooming in on images and so on within the reasoning process. So this looks like somebody attempting to give us a recipe for training these tool-in-the-loop type reinforcement learning models. So they propose retool, long-form reasoning with tool-integrated learning. Dynamic interleaving a real-time code execution. So Python is one of the most fantastic tools if you're training a reasoning model, right? Because it can offload the actual computation of like big multiplications or something like that and use libraries like SymPy. And then an RL paradigm that allows us to do these rollouts with this code execution and get feedback from that. So I'm excited to see exactly what their framework looks like. I've got a somewhat of a picture in my head, but let's see how they go. And then they're going to evaluate this on MathOlympiad benchmark, AIME, getting 600%, 67% accuracy with 400 training steps. And remember, I think the paper 2 ago that we looked at was reporting possibly even higher accuracy than this. But we'll see. This feels like maybe this one might be something that's a bit more broad. If you're imagining like, oh, we're training it to use code and so on to perform like general reasoning, and that happens to apply really well in this math benchmark versus like we only train on Math Olympiad questions and then it does well in Math Olympiad. So yeah, we'll check it out. Looks like they find an improvement from their version. What do they call this? CI code interpreters, right? So having a code interpreter in the loop, they see a much larger growth in accuracy versus just the baseline, which is just text-based only RL. And this holds up even for the even newer, even less contaminated version of this benchmark, starting from a Quayan model. Okay, so let's check out how they inject these code interpreter and other tools into the training process. And specifically, like, how does this work for the training? Because it's not like you can backpropagate through code execution, right? So we're going to look at how they're assigning the reward to the rollouts that include this interleaved code execution. Okay, so I'm going to skip through until I see like a system diagram or something. Here we go. Okay, so I have a question. We are normally going to roll out and produce multiple completions. This would then get a reward, we'd compute the advantage, and then we'd update the LLM based on that advantage. And so, for example, with GRPO, the reward would be, the individual rewards for all of them, and then the advantage would be scaled based on the group. But some other ones might have some other methods for computing this advantage I haven't seen. Okay, so they're using proper PPO, so that uses a slightly more complicated method to estimate those advantages, but that's fine. Okay, so that's the text-based one, and then the rollout with tooling is to have the language model produce some outputs, and at some point it'll be a piece of code that it would like to execute in some specific syntax, and then the code is going to get executed, the results are going to be injected back, and it's going to continue sampling, right? So I produce some tokens, I send some code to be executed, I get the code back, I produce more tokens, I produce more code, I get the result back. And so you can imagine the model saying, okay, I'm looking at this problem, I'm going to start by importing SymPy and checking that I can set up my system of equations. Okay, cool, that passed without errors. Now I'm going to solve the equations and look at the, the zeros. Okay, cool, I've got those back, and I'm going to pick the one that's positive. Here's the final solution, right? And that's going to be this final result that gets the reward, and that updates the model. And so they're going to have some clever infrastructure needed for handling these code execution requests and inserting back the results. But then they're doing PPO on that, and they modify it during training. They have a rule-based outcome reward to enable the model with the flexibility to autonomously explore and develop codes. Okay, so in other words, the reward is based on whether or not you get your final answer, which gives you flexibility to use the code sandbox if you like. And importantly, for things like this, one thing that's interesting is you kind of have to start with a model that's competent enough that it can reasonably use the tools or use the format that you give it. So you'd start by prompting it, hey, you can use code execution by producing code in this syntax. Maybe early on you have a reward for correctly producing that syntax. And then, as long as your model is able to start somewhat accidentally or explораtorily producing that occasionally, those ones will get high reward if they're accurate, and it'll learn to do that more and more. Reward design, 1 if the answer is correct, otherwise -1, nice and simple. Their rollout approach dynamically supports interleaved code. They have a prompt template, here we go, that uses these code tags, and then they fill out these interpreter tags. And so, unlike, you can imagine supervised fine-tuning, I I wonder if they train on what's between these two tags, because if you imagine like, okay, I do this rollout and then like training on that just in like a naive fine-tuning way, I'm just saying like learn to produce sequences like this, which could include like faking these interpreter sequences. But instead with PPO, you're doing the whole rollout, you're getting a reward, and then you're assigning back that you're using that reward to update the whole to try and make the whole completion more likely. Yeah, so we'll see how they do it. Oh, interpreter feedback mask, fantastic. They mask out the output from the compiler so that they're saying, look, don't spend your compute learning to produce code outputs, right? Learn to produce everything around that, and we'll mask out this section. Okay, I like that. To reduce memory costs, they cache the KV, and then they do the code execution, and then they put the whole block through. Okay, nice, efficient. They use an asynchronous code sandbox environment with workers in a pool, and they're just submitting and pulling these out. Yeah, so this is a nice, you can see this is a big lab. They've got more investment to work on this kind of custom infrastructure. They're working with a slightly larger model, or I guess a much larger model than the 1 billion parameter one in that previous paper. They are, all of this stuff is not like, oh, this is for one paper and then we're going to throw it away, right? You know, this is by dance. They're investing in training language models, training reasoning models, training them to do tool use for things like search and browsing and image editing and all these other things that are going to be downstream. So it's worth them building up this infrastructure for spinning up sandboxes for quick code execution, for getting efficient KV cache reuse during reinforcement learning training, for having a good, reliable PPO implementation that they can apply to different cases. So that's, yeah, all very cool. Virl is a nice, I think it's an open source framework that was like one of the early ones to do this. Maybe they did gRPO with tool use. I will check it out. Oh, okay, no, this is by ByteDance. My bad. Let me switch share. Hopefully you can see. Okay, so this is actually their RL training library, and with a community around it. Fantastic. Okay, so back to the paper. They have some baselines. Then their code interpreter powered RL gets a significant boost over those baselines, and they do some ablations. Instructor cold start is probably, cold start generally means like fine tuning with some examples to get it going of following the specific syntax. And then text-based RL would be doing the same thing on this model but without the code execution feedback. And you can see that gets that's better than just the base model, but it's not nearly as good as the retool versions. Okay, that's pretty cool. It learns to use code almost 100% of the time to solve these problems, which is interesting, but it makes sense, right? If you're doing these mathematical problems and there's certain steps in there that involve computation, right? Addition or solving equations or so on, better to learn to offload that to the deterministic fast computation, right, of actually executing code versus trying to do that with sort of mental arithmetic in the language model itself. And over time, it's learning to use more and more lines of code. The code passes tests, and yeah, pretty cool to see an example of this kind of like augmenting language models to make up for something that they're not great at, by, yeah, giving them extra tools. I feel like this is actually a really powerful way to boost performance, very, very generally. Okay, so here's an example. They have a problem. They are tackling the problem step by step. They try and execute some code, and they get an error back. Oops, let me correct that. They redo some code that includes importing NumPy, and then so on and so on. This will be more reasoning that gets the result back from that and gives the final answer. Okay, so I'm not going to spend too much more time on that, but it seems like that's really great work, and I feel like there's probably a few more ByteDance papers in my stack. I'm just going to pop over to the stream, see if there's any questions. Okay, pretty quiet on the stream front. I did tweet it out. Cool, well, we're ticking off these, and that's the main purpose, so I think I'll just continue. This next one, I'm slightly torn. I might just do a separate video on this. JetFormer. autoregressive decoder-only transformer that tries to maximize the likelihood of raw data, understand and generate both text and images, and they use normalizing flows. Yeah, this one might be worth breaking out into a separate discussion. And I feel like this plays into a theme I'd like to cover in a separate video. Okay, so we're going to save JetFormer. And we're also going to save the large language model to diffusion fine-tuning. I feel like these two actually form a theme, believe it or not. Okay, so we'll leave those. Back to another reasoning model related paper. I guess that's the theme of the ones I put in my Zotero but don't read. Okay, reasoning models have done remarkably well. They suffer from overthinking. They do reasoning steps even after they get to the right answer. Can we spot when they've already gotten to the right answer and save some tokens? And so they're going to try and create a probe that can verify whether or not the model thinks it's right and maybe give you early exit. So they reduce the number of inference tokens without compromising performance. Seems like a cool idea, right? You've seen this if you've read the chain of thought. Often the models will reason, come to some conclusion, and then say, but wait, what if, and so on, and then they'll get back into another long spiel. Okay, so let's see how they do the probing, and then move on. Okay, on the left-hand side, the chain of thought is passed into multiple chunks, each corresponding to a reasoning path. So my question is, how do we find the chunks? It contains an intermediate answer as a termination. Okay, so they're somehow going to identify that he has none left is an answer. And then on the right side, representations for each chunk are obtained. So the next question, how do we get these representations? And probed to predict the probability of the answer being correct, right? So we're going to find where it has intermediate answers, and then we're going to score whether that answer is correct or not. And we're going to get the representation of somehow the span or the chunk. And then we're going to try and learn a way to map that representation to a probability of being correct. Okay, so let's see, how do they find these chunks? Split into paragraphs. Cool. Identify the start of a new reasoning path by finding keywords. And they've got an appendix. We can take a look at that. Wait, double check, alternatively make sure. Another way, verify to confirm. Cool. They use Gemini Flash to get the intermediate answers. Okay, so nice cheap model for like effectively structured data from unstructured text. Adjacent chunks are merged with the closest chunk that contains an answer. So each chunk now has an intermediate answer and a label, right? This is like the chunk and the final answer, I guess. Yeah, each C is part of the reasoning trace, and Y is the binary label indicating the correctness of the answer. Okay, then we feed the chunk, and we take the last layer hidden states on the last token position, which is interesting. So when you're extracting representation from language models, you're looking at hidden states based on some input token. But I know it's not necessarily obvious where that's going to be, right? So if we find a reasoning trace, it's got to be some example. Okay, imagine this is our reasoning trace, right? Then, or alternately, or so on, they're saying we're going to go to the last token of the previous chunk, and that's where we're going to look for our hidden state that represents like a certainty. And this sort of makes sense, right? Because this token here, if we're saying the next token is like alternatively or wait or one of those like pivot phrases, it's going to be preparing to predict that next phrase, right? And so the odds of that phrase resulting in wait or on the other hand versus the odds of that phrase resulting in okay, final answer, that is going to be loaded on that token. So that does make sense to me as a place to look for the representation, but I'm not sure whether that's necessarily like the only answer. You could also say like, why don't we feed the whole chunk through and pool, or why don't we look at the pivot token after that, right? So like let it generate the word alternatively, and look at this one, its hidden states, to see whether this is like, oh, is this an alternatively because I'm about to I agree that this is a good answer, or is this a okay, I should definitely check something else because I think that previous one was wrong. But they're going to look at just the last token of the chunk, which is fair. Okay, so we said they're collecting the data, they're training the probe, and so then we have this last hidden state. Also, people, public service announcement, don't use the last hidden state, right? Please use like the second last or the third last layer. This is something I need to write more about and share more about, but when you're working through the transformer, like the intermediate states are incredibly rich representations, right? And they're used to bring in more information from other parts via attention, and then they're augmented by the MLP layers. It's very, very rich, very interesting. And then right towards the end, like the final layer and then the language modeling head, that gets collapsed down into next token prediction. Right, or in like, say a clip model, again, you've got this like really rich representations of each token patch, each image patch feeding all the way through, and then they kind of get collapsed down because they get pooled, and then they produce a single embedding vector. So it tends to be that the last layer representations are sometimes more different than, say, the third last layer or the second last layer. Those are going to be very similar, and possibly slightly better as a choice for this kind of probing. Anyway, just throwing that out there. Completely unsubstantiated until I write up my findings. Okay, so anyway, they're using the last hidden states. That's actually probably totally fine. Just getting on my hobby horse. Cool. Okay, so we now want to say, can I map from this last hidden state to, is this the correct answer or not? And so they train the probe, a 2-layer network, right? Really little MLP. And this is the data's imbalance where most answers are correct. Wow, okay, cool. You've got an easy data set, I guess. So they use a weighted binary cross-entropy loss. So it's a very, very small little model, right? 2 linear layers and a ReLU and cross-entropy loss. So pretty nice. And let's see how that probe does. So on GSM-8K, using a reasoning model, and it's going to do a lot of weight, think, verify alternatively, etc. They're going to run through training set, validation set, etc. Okay, and so in domain performance of the trained probes, each probe on the test set from the same data set. So if I go through GSM-8K, I train my probe, and then I go through the test set of that. That's what's going to be reported, and then we're going to do this for in domain and hopefully out of domain. Okay, and our accuracy here, or our area under the curve rather, for all of these seems like it's high. It's learning something. It's able to predict for different models with different accuracies. So this is Quen32b on this particular problem, really, really accurate at predicting whether or not the intermediate answer is correct or not. So you're able to pull some signal out of that. And so then let's see, out of distribution. So training on GSM-8K and then working on math, you have still pretty good performance, but not amazing, right? Like in this case, not doing too fantastic at all, but still some extension, not just on exactly the training data you did. I guess you could train on a mix of everything and see how that did. Encoding of correctness is related to the reasoning abilities, so maybe better models are also more useful at this prediction. Interesting. Correctness can be detected before the answer is generated. So, okay, so they do look at other positions starting from earlier within the chunk. They look midway through the reasoning chunk and before the answer is even generated to determine if it's like knows that it's on the right track. And it seems like our error goes down and our area under the curve and accuracy go up as we get towards the end of the chunk, but even early on, they're doing not too bad. Okay, so that's all the baseline. We have this mechanism to probe the model whenever it produces an intermediate result and guess whether or not this is actually something we should stick with as our final result. So they're going to do early exit. They start sampling, and then confidence-based early exit whenever you have above some threshold for model confidence that you know this is the right answer. You can exit out. And so let's see, confidence-based early exit, where one would be the same length as the non-early exit samples, potentially. If I stop whenever I get something that I'm even 0.2% confident is 20% confident is the correct answer, my accuracy is nearly 75%. And then as I boost that threshold, as I say, I want to be more, I'm only going to do early exit if the model confidence based on that probe is high, above 80%, then my accuracy on the task is increased, but I'm also using more tokens. So there's kind of a trade-off that you can do to say, I'm going to exit as soon as I get anything that even looks vaguely like a correct intermediate result. I'm going to get some accuracy, or I'm going to wait until I see like a 90% assigned probability that this is the correct result, and then I'm going to stop it from overthinking. So yeah, seems like a pretty useful trend. Notably, like this static early exit would be like, let me just set like a maximum number of chunks or a maximum number of tokens, and just say, look, I'm only going to let it do 4 reasoning chunks, and then I'm going to exit. And you can see it gets the same kind of trend, right? The more chunks you do, the better. But we're doing a sort of slightly worse trade-off than using this like confidence-based approach. So I could just say, look, I only, let's say, wait 4 times, and then that's done, and it has to use what it's got. It would be better to say, look, sometimes it's not going to be very confident even after 6 waits, 6 reasoning chunks. Sometimes after 3, it's going to be confident. And so if I use a threshold, on average, I'll use, less tokens than if I just always did 4 chunks, and my accuracy will be better. Okay, so that's pretty cool work on early stopping, and maybe a potentially interesting way when people are setting reasoning budgets, low, medium, high, or something like that, to use something like this rather than the pure like token counting based methods that people are doing. All right, any questions in the chat? All right, my voice is already feeling a little scratchy, so this might only be like an hour-long stream, and I might step through a few of these more quickly. So here's one that we might just skim on the generalization of language models from in-context learning and fine-tuning. So this is getting at a really interesting question. I remember seeing maybe a thread about this on Twitter. When we fine-tune on something, is that the same kind of learning as if we had that text and context? And which one's better? Are there pros and cons of each? And this is a big question for things like if I want to adjust a model to my own use cases, if I fine-tune it on my data, if I don't ask the questions in the right way, I might not actually elicit anything that I trained during fine-tuning. And so it might not actually give me the result that I want, versus having the entire thing in context that might be very computationally expensive to be, constantly working on these long context queries, but it has it right there. It's able to use the full power of the attention mechanism and in-context learning to pull out references to that data, including like ways of reshaping it and understanding it more thoroughly, potentially. So I'm interested to see which side they come down on. So they say language models in context learning shows different inductive biases and can generalize better in some of these cases. So they explore these differences with some different data sets, and they expose pre-trained models to subsets of the information in these data sets that they curate, either in context or through fine-tuning, and they evaluate the performance. So let's see how fast we can skim. Data sets, simple syllogisms, they do some work in the reversal curse, semantic structure. Multiple choice likelihood scoring. They're fine-tuning 1.5 Flash, sharing their training stats. Nice. Okay, so let's see if we can see some results. Here we go. So reversal curse, pre-trained, fine-tuning, accuracy actually drops below chance. In context learning, it does really well. Augmented fine-tuning, it does really well. Okay, so this is going to be an extra interesting thing we should look at. They don't just compare these two, they have some sort of suggestion for augmented fine-tuning. Let's find some other results. Syllogisms, again, fine-tuning, less than in context learning. less than whatever this augmented fine-tuning is. And I feel like I remember what this is, so we'll get to that shortly. Okay, so yeah, more examples. Same sort of trend, same sort of trend. They've got a very standard picture here. So what is augmented fine-tuning? And I think the answer is a lot of synthetic data. So we propose to bridge the gap via dataset augmentation, prompting an LLM to generate augmentations of the dataset in context, and then adding these augmentations to the training set. And these dataset augmentations can bridge the gap. So what this is getting at here is if I have some statement, right, that says the fleeble of a foo is bar, right? Like it's a complete nonsense sentence. If I said that phrase and that phrase only, and I fine-tuned on that, it's learning to increase the likelihood of predicting the next token correctly, right? So if you prompted with the fleeble of a bar is what, it might be able to predict flu, right? It's able to like see that this is a similar sequence to something that it was trained on, and predict the next word correctly. But if I said, what is a flu's fleeble, right? Or which item's fleeble is a bar, some sort of rephrasing or reversal or inversion of that question, that's not a sequence it's seen. And so via fine-tuning, it's much harder to elicit that fact because it's never been phrased in that way or any way similar to that. Now, if that whole sentence was in context, right? When I ask that question in any of those ways, those keywords are able to attend to the earlier sequence and pick up that, okay, I'm asking about a fleeble, I have this earlier thing that references that in relation to a flu. It's able to like tie in that data and produce that answer, even though it's maybe asked in a different ordering, right? Because attention is really good at this kind of like merging in prior information and attending to those different tokens. So that's a clear case where the in-context learning might be better than the fine-tuning. But even better than that, potentially, it seems like what they're saying is if I took that one sentence and I used a language model to say, look, rephrase this as many ways as you can, flip it around, turn it upside down, right? Show me question and answer pairs where someone asks a possible question about this fact and then what the answer would be. And it's able to use its in-context learning power there to generate those different like paraphrasings. Look, they also do the kind of silly nonsense sentences I was just talking about. Yeah, do all these paraphrasings, and then fine tune on all of those different ways of saying it, right? So try and get much more bang for your buck from the sample. And so, yeah, so they've got some random made up entities, and then let's see the augmentations here. Yeah, fine-tuning with data augmented in context inferences yields similarly high. I feel like this is the key takeaway of this paper, but I want to see the actual details of their augmentation. Okay, maybe that is it. Maybe they don't have a section on the augmentation, but this is a key idea, right? People talk about synthetic data and oh no way you can get further with synthetic data. The key here is that this is not purely synthetic data. It's synthetic data based on some seed of real data, right? So I take in one fact, and then I paraphrase it in a bunch of different ways, and I reverse it, and I do sort of in-context reasoning about it, right, at training time. Then I train on all those different variants. I'm able to get much better performance. And so this is the key. We're doing this synthetic data, and we're improving performance, and seeing that downstream as good or better than in-context learning. And so this is like a big deal because it means that we could potentially get a lot more use for any, like, imagine some hyper niche, like there's one blog post on this topic. I could train just language model training on that, and the model might maybe, if it's a really big model, happen to pick up some little fact about that, but it's not going to know it, quote unquote, right? But if you took that blog post and you took a really smart model, put the blog post in context and had it reason about it, ask itself questions about it, answer those questions, think of other implications, link it to other like related blog posts, and then you trained on all of that, you'd probably know it a lot better. Okay, so that's a really, really fantastic, really well put thought, I like this paper. I like this paper a lot. Well done, Google. Still checking for questions. Still nothing so far, but if you are watching, feel free to, steer the conversation. Okay, so related to that, actually another DeepMind paper, but this one in collaboration with ETH Zurich. How do large language models learn facts, dynamics, curricula, and hallucinations? And I think this next one is also related, how new data permeates LLM knowledge and how to dilute it. So you can see it's kind of a theme. Different groups potentially, but still looking at this idea of, where does learning come from in language models? How did they learn these facts? Where did they come from? Are there better ways to do that? So these two someone shared, but I can't remember where. Maybe it's my friend Raja. Okay, large language models, they accumulate vast knowledge during pre-training, but we don't understand exactly how. We're going to create a synthetic factual recall task, and we're going to find three things. Language model, learn in three phases. They have a performance plateau before acquiring precise factual knowledge, which is attention-based circuits supporting recall. Then the distribution of the data during training affects these dynamics. Imbalanced distributions lead to shorter plateaus, and hallucinations emerge simultaneously with knowledge, and integrating new knowledge through fine-tuning is challenging as it quickly corrupts its existing parametric memories. Our results emphasize the importance of data distribution and knowledge acquisition, suggesting novel data scheduling strategies to accelerate neural network training. Okay, so I'm going to explain this having only read the abstract. I'm going to explain why this fits a lot with my mental model of language models, right? So we're starting out, we're trying to predict the next token on a bunch of text. And initially, our predictions are completely random, right? We've initialized this network with random noise. The predictions are completely garbled, so our loss is very high, and we're not learning anything. Very quickly, the first thing the language model is probably going to learn is stuff like token statistics. So if you just predicted the word the for every next token, you would do a lot better than predicting the word dodo, right? Something obscure, some unusual token, a solid gold magic carp 73. And so you're going to very quickly, before you learn anything else about language, probably start to put more likelihood towards more common tokens, right? Very soon after that, you'll see emergence of common bigrams, right? Common phrases. Thank you very much might be like those kinds of like very simple patterns start to emerge. And while you're learning that, you're a mostly randomly initialized model. You're just starting to get some like basic language statistics. If a piece of data comes by that encodes some like really obscure fact about like the interaction of two chemicals that's only mentioned 2 or 3 times in the internet, it's unlikely that that's going to contribute much to how you're doing on the loss. And so those kinds of like, specific facts that might eventually come up again, it seems like you would want to first settle into having learned some of the like quote unquote basics of language before those other pieces start to become, players within the scheme of what's contributing to the largest like parts of the loss. And so that would make sense with what they're saying here. We would have like this performance plateau, right? We'd like rapid increase in performance, and then that would start to like slow down as you solve all the easy ones, and you have to start learning more and more complicated pieces of machinery to do things like in-context learning, right? To use information from early in the passage for later, rather than just relying on word statistics, and also to then like use more and more specific facts, not just that like, U tends to follow how R, but instead much more like complicated things like the capital cities of different places, or these kinds of like much deeper, more specific, less common facts. Okay, so that sort of makes sense. The final piece, the fine-tuning, is a little bit different because it's often hard to separate like what is fine-tuning and how is that different from continuing to train, right? There's sometimes nuances to do with like the learning rate schedule and so on, but it seems like often fine-tuning is just continuing to train the same way you were doing the training, but to it's already had a lot of training. And so if they're saying like there's this plateau, then we start to acquire factual knowledge, and then maybe the available circuitry for memorizing facts becomes saturated, right? Especially for smaller models, or your learning rate is tapered off, so the dynamics get more and more like fixed in, and large changes would have, you know, a more destructive effect as you've tailed off towards the end of training. Then you try and do fine tuning with a much higher learning rate again, and suddenly like you're erasing pre-existing facts or something like that. And so I'm less sold on the fine tuning has to be destructive part of these three phases. But it's interesting to see this kind of like broad scale structures, plateau in performance, and then starts to learn these individual facts, which aren't going to change the loss much, right? Because you learn something like the, you know, Latin name of a plant, right? That might only boost your performance in 3 other times during the whole training. And so the average change in the loss from learning that fact is going to be extremely tiny, but there's going to be a huge amount of those facts, and that's going to, in aggregate, improve your performance, but much more slowly than learning word statistics will. Okay, so they're going to set up some artificial biographies for factual recall. They're going to train on this, analyze the data distribution properties. Okay, let's see if there's any like takeawayable pieces here. Synthetic data, measuring knowledge. Okay, so they'll ask questions. This is a good one, how to distinguish knowledge from memorization. So memorization might be like, it's memorized a specific phrase or something like that, versus like, oh, it's able to answer reversals and rephrasings of some question about some actual unit of knowledge in here. Yeah, very hard to tease it apart. Okay, training steps. Loss drops really quickly at first, and then very slowly over time. Accuracy about these attributes starts out near 0 and continues to be near 0, and then slowly but surely increases during training. The end of this plateau, like I guess somehow measuring this point or this point, the more individuals, the higher number of steps this is. Okay, so this is something I'm not sure about. I guess this is all training from scratch. Why would more individuals shift this further and leave you on the plateau for longer? I'll have to think about that. If you have any ideas, put them in the chat. Okay. They do some attention pattern surgery. More trained the reference model is, the better the attention patterns are for the modified model. And these changes happen mostly during the plateau. Okay. Interesting. So they say making this imbalanced, right, having some individuals appear more frequently, reduces the plateau. And this, I guess, we can build an intuition for by saying, if we had like randomly shuffled this, or we were never repeating individuals, then there'd be less incentive to do any particular piece of memorization, and also to build the machinery that let you do that. But if you're seeing right at the beginning lots of repeats about James and various attributes of James, right, like one individual, then the relative like contribution to the loss of being able to memorize just that one fact is going to be higher than any one would be for, you know, if there's lots of different individuals. And so it makes sense that by starting out with some imbalance and some particular individuals appearing more frequently, you build that machinery earlier, and then later on the model's able to benefit from that for any other individuals that come up, and so you overall get this improvement happening earlier, versus if it was having to build that machinery based on very sparse signals from very rarely repeating individuals or facts. Okay, that makes sense. hallucinations emerge simultaneously with knowledge. It's like something like, oh, as you're adding existing facts, you're also adding pieces that encode maybe incorrect facts, and trying to train in new data might only erase some of the, might leave those hallucinated facts in, or might leave less machinery available for learning those new things. I'm not too sure exactly how that plays. We could look at this in a lot more detail, looking at how they measured hallucinations and so on, but I think that's a good interesting read to see, like, okay, yeah, let's attempt to study these dynamics, and yeah, it's fun to like compare to your intuition. I'm not going to spend too much more time on that. Okay, and this one looked similar. How new data permeates LLM knowledge and how to dilute it. Okay, so learning a new fact causes it to apply it in unrelated contexts. They have a special data set of text samples to probe. They find some measure of how likely priming, in other words, bringing up some fact even when it's unrelated to some other fact, and they look at token probabilities to predict this. And they have a way to modulate how this knowledge affects existing behavior. Text augmentation strategy, interesting and tie back to that other one, and ignore K update pruning. So the question here, I guess, is if I'm wanting to fine tune on something new, how do I avoid it then like overpowering things and having the model only want to talk about that fine tuning thing? And the answers are going to be maybe producing more data. So rather than training heavily on one sample, you could train very gently on multiple rephrases of that sample. And then also maybe like looking at your updates and not applying all of them. So when you're training on this, maybe avoiding overly aggressive gradient updates. Okay, so that's my guess. Let's have a little skim. This one I'm not like as invested in. I've got the data set. They have some scores for priming and memorization. As it memorizes more, it also tends to bring that up in unrelated conversations. That makes sense. Putting these in context, does this also prime? Less so than when training with weights. Interesting. Okay, so here are their strategies to modulate the impact. Modulating the keyword probability by maybe like elaborations of the sentence, using different intermediates, different words, so that you don't just always have like the one word being used again and again. You have like different variants. That makes sense. And gradient pruning. Important updates are quite sparse. Even just 10% of the top updates are enough to preserve task performance. What happens if you only keep the top K% of parameter updates? Okay, so it's not pruning away the largest updates, it's pruning away everything but the top 15% of updates, and hoping that the other ones don't mess up everything else or skew it too consistently. Oh, okay, no. So we kept the next highest 15%, right? And everything else was zeroed out. They observed reduced priming. Okay, so it was what I thought at first. They ignore the most extreme 15% of the updates, but they keep the next 15% or keep some other like strategy. Removing only the top K%, and even removing 4%, decreased priming relative to no pruning. Okay, and it was still able to memorize, but it didn't do the priming stuff. Okay, so that's actually a pretty neat idea, is to say when we're doing these gradient updates and we look at the largest K% of the weights getting updated, the ones with the largest gradients, let's ignore the top 8% of those, right? So the most extreme updates, let's prune them. I guess you could probably also investigate clipping these instead. And then via the rest, right, of those somewhat sparse and lower updates, you'll still learn the thing, but you won't learn it as extremely, and it won't be like so aggressively changing the model. All of this stuff I feel like very coupled with things like the learning rate that you're using, whether or not there's a schedule, and all these other pieces, which are never like necessarily easy to completely search over. But it might be nice to say like, oh look, we're seeing all this stuff when we're training. Did you try training at a lower learning rate? Right? Who knows? But it seems like that. I mean, I would guess that at least done some due diligence there. So it's good to know that there's this trick or two. If you're training on some data, don't train on the same data over and over again. Do some augmentation, right? We saw that in the last two papers from Google as well. This idea of like extending one sample into many via rephrasing and so on, being a very useful technique in general. And then the second thing, if you're willing to tweak some knobs when you're fine tuning, if you don't want to then like overpower with that fine tune, you want your model to still be a very general model, just with this new piece of update, some new knowledge, then potentially throw away some of the most intense gradient updates every step, and you'll have less like hypersaturation on one task. Obviously, this would work in combination with all the other tricks, right? Mixing in some amount of the pre-training data or more diverse data in with whatever you're fine-tuning. You know, not using too aggressive of a learning rate, not using too many epochs, etc., etc. Cool. Okay. Any questions before we switch gears and look at a image model? All right, I'm going to continue. We present CGEM3, high performance bilingual image generation foundation model. Effective techniques, mixed resolution training. I like, big fan always. Cross modality rope, representation alignment loss, resolution aware time step sampling. All very good ideas that I remember fondly from my diffusion days. Aesthetic captions in supervised fine tuning, reward model, aligning with human preferences. This looks like a really good recipe for a decent text-to-image model. Cool. Let's have a look at the pretty results and some of the details. Defect-aware training paradigm with a defect detector to avoid particularly warped things. And also worrying about watermarks, overlay text, etc. Data distribution, optimization. Okay, model architectures. They use a VIT. Oh wait, do they? Yeah, DIT. So that's a diffusion transformer. With maybe this is something to do with being masked and using some kind of discrete diffusion. We're not sure. Cross-modality rope. So how do you do position embeddings when you have text tokens? Okay, they do 2D rope on the text tokens. Cool. And then they do their pre-train to get the like general capability to produce images, but not necessarily high quality. And then they work through their different techniques to get a final model that's more aligned with human aesthetic preferences and following the prompts and all these other types of rewards. It's pretty cool to see the succession here. Yeah, so this is what you get if you just generically generate a train a model on internet images or some subset thereof. And then as you're like slowly aligning with, okay, let's train only on good samples, let's use some human feedback to incorporate that as part of a reward or something. We'll see what their PE is. Okay, training objective, so flow matching, nice. So you're trying to predict the image minus the noise or the noise minus the image. I always get them confused. A representation alignment loss is something I've been meaning to look at, but not today. I know ClinofSimo has a good write-up of that somewhere that I've been meaning to look at. Representation is computed as a cosine distance between the intermediate features of our model and the features of a pre-trained vision encoder. Okay, so it's saying, look, we want to produce useful intermediate features for our task, and rather than just having them learn those features based on this flow matching objective, we're also going to have them try and align with some similarity to the features of an existing good vision encoder, right? So Dino is trained self-supervised to learn very useful representations of images, so we might as well try and copy those representations somewhere in the middle of our model. And introducing this alignment can accelerate the convergence of our text-to-image training. Interesting trick. Cool. Okay, we're sampling time steps. The larger the resolution, the less of the signal is going to be obscured by a given amount of noise. See common diffusion noise schedules are flawed and simple diffusion papers for more on that. So we want to shift the distribution to increase the chances that we have lower signal to noise ratios. In other words, more noise when we're doing higher resolution, so that we erase more of the actual signal rather than just the fine details. And so then they have this way of, during training, picking the distribution based on the resolution of the images. Fantastic. Detailed captions with aesthetic terms, post-training with aesthetic captions, reward models. So they used Clip as a reward model previously, but now they use VLMs. I guess that makes sense. They've got some good VLMs now. And they formulate them as queries and derive the rewards from the normalized probabilities of yes. So here's an image. Is this a good image? Yes or no? And the model predicts some probability on yes, some on no, and you use that as your reward. Right? Really nice way to turn an existing VLM into like an image goodness classifier with just a prompt. Okay, they have their acceleration, stable sampling. It does good, right? I think this is like highly performant, up there with the best of the best, if not the best. There we go, top of the leaderboard there, but very close to OpenAI and Recraft and some other players. So fantastic stuff. Does well in human evaluation, etc., etc., etc. Okay, very impressive paper, very impressive model. I believe you can use it in various places online. But cool to see. This feels like a good recipe, right? Use a big transformer model to do flow matching, conditioned well on text. We have this representation alignment trick. Pay attention to your noise schedules and how they vary with resolution. Fine-tune on a bunch of data, train on a bunch of data and then fine-tune on aesthetic data, possibly with synthetic captions, and then do some RLHF, but not too much. Yeah, this feels like a good general recipe for a state-of-the-art text-to-image model. We'll see how long the sort of race continues. I know the larger and larger and larger multimodal language models, just next token auto regression like GPT-4o, these are just getting better and better at the image generation part. And so bringing some of these ideas in, right, training on general data and then fine-tuning on aesthetic data and optimizing for image aesthetics and so on might continue to boost these. So we'll see how long the kind of like flow matching style sticks around, but cool to see it's still holding its own. Great paper. Oh, okay, training flow transformers in ambient space. What is this about? Flow matching models. Okay, and then rather than having a VAE and then working in latent space, we are introducing ambient space flow transformers. Okay, not entirely sure what this is about, but I'm going to put this with JetFormer as something to look at later. Okay, changing tack, inspired by discussions with my friend Benjamin, who did a lot of the work on the modern BERT model. GPT or BERT, why not both? Fantastic idea. Take the same model backbone, and then toggle whether or not you're using a causal attention mask and doing GPT style training, or using the bidirectional BERT style masked language model training. Both have been tried, both work well. What if we combine the two? And the nice trick with this is that when you're doing GPT style training, every single token is getting a loss, right? Because for every token, you're predicting the next token. So in one forward pass during training, you learn from every single token in your sample. It's very rich training signal. The masked language modeling, you only predict for the masked tokens, right? So you have less signal per sample, per forward pass, but you're learning different things. You're able to do the bidirectionality, and you're able to get this like more flexible mask prediction model. So yeah, I'm hoping we could maybe try this, maybe even try mixing in prefix LM as well. That was something he seemed interested in, so I'll update you if that works. But yeah, very cool idea, nice implementation. They do it fairly small scale, but they find that it works well. So yeah, I really like that idea. I really look forward to seeing it tried at larger scale. Moving on. Simple AR. Pushing the frontiers of autoregressive visual generation through pre-training, SFT, and RL. Okay, so this is another text-to-image model, but we're doing autoregressive generation, right? So rather than doing the flow matching and using a DIT type approach, we're doing one visual token at a time, as it were. Okay, so let's see how they do it. Small model, generating up to quite large images, and doing pretty well, apparently. And it takes a little while to sample, but by autoregressive standards, to generate a large image like this, that's not actually bad. Okay, so questions that I have: how do we model the image as a sequence? Like, are they doing patch to embeddings, or are they using some sort of like VQGAN? What is the representation? Okay. We tokenize it into discrete visual tokens using a learned tokenizer. Cool. Probably okay, some previous model that they've worked on with some compression ratio. Okay, so very much like VQGAN, which I guess is probably something like this. Nope. Okay. Wow. I guess the field's come a long way, and there's various intermediate works. We concatenate text and image tokens, and then we put them into a decoder, right? So very much less of a custom, carefully crafted weird model, more like turn the image into tokens and then model the text and image tokens as a sequence. But we do the same thing as a lot of other good models these days. We start with pre-training on a big data set, then we do some fine-tuning, then we do RL, and these days everyone is using GRPO, the rage, thanks to DeepSeek. And so we're going to use that with some reward, and the reward will be clip as a reward model. Cool. Fantastic. Okay, I think that's pretty much the main bits of this. Are they initializing from an existing language model? Slight improvement with the language model initialization. That's nice. I like initializing from something rather than nothing whenever possible. But it doesn't have much effect. I think this is because the text prompts are simple, and maybe if you're doing a larger model, using an existing LLM might be better. Okay, they try some different positional encodings. Do they get much difference? Actually, this looks like the 1D positional embeddings are slightly better, but I wonder how they did the text versus the image embeddings and so on. Who knows? GRPO, I guess maybe slightly better or more aesthetic somehow. Definitely getting higher reward over time, but it's easy to get reward hacking when you're trying to do RL on diffusion models, image models in general. I find it needs to be done with a light touch and careful design. Otherwise, you can like reward hack your reward model pretty easily. If you want to see a fun example of that, let me switch to the main screen and look at rainbow diffusion, hugging face. This is a stable diffusion variant. Oh, it no longer has the image previews. That's really sad. Yep, trained with a aesthetics-based reward model. Reward hacked it. Anything you generate has lots of flowers and rainbows and unicorns. It's quite fantastic. Okay, cool. Simple AR, giving us a nice, simple implementation of the general idea of take a bunch of text tokens and image tokens, model them as a sequence, and you get an image generator. Fantastic. Okay, wait, here we go. Learning adaptive parallel reasoning with language models. Intimidating, but we're down to a visible number of tabs. Okay, how do we scale inference time compute? We can think for longer, serialized chain of thought, Parallel methods suffer from insufficient coordination, right? So if you do n things in parallel and try and merge them together, you get a lot of redundancy. Adaptive parallel compute, their solution enables them to orchestrate both serial and parallel components by enabling like this kind of idea of spawning and joining operations. Okay, so rather than producing one long chain with lots of backtracking, or producing 10 chains in parallel, 5 of which might be identical, and then trying to combine them, they're saying we're going to produce a chain that somehow allows it to spawn multiple instances of itself to explore different ideas. And they have some sort of constrained experiment, and they show high performance at the same context window. So let's see exactly how they do the splitting. Okay, here's theirs. It does some inputs, and then it's able to somehow spawn 2 children, and then join them and see what their results are, and pick the one that it likes. It seems like that's the key. It seems like that's all I'm going to look at for this paper. If you're really excited to look at it more, I'm happy to revisit it. Let me check the chat. All right. Check a message soon if you really want to see that paper. Otherwise, you're going to go on. All right. Back to the vein with those Google models and the data augmentation, taken to the extreme, reinforcement learning for reasoning in large language models with one training example. RL with verifiable reward with a single is good at elucidating the mathematical reasoning capabilities of LLMs. They do it on a single example, which boosts the performance from 36% to 73% on the math benchmark. Okay, so this is somewhat crazy and very impressive. We see a general lift across different benchmarks as well. And so rather than using thousands of examples, we just use a single one. And they see the same across different models and RL algorithms and so on. Okay, so what is going on here? Yeah, what does this tell us about reasoning models more generally? Let's think about this a little bit. Post-saturation generalization. Okay, so let's talk about what might be going on here before we look too deeply at the paper. And it relates to this idea of the elicitation hypothesis. And this is a term I believe I first saw it at least in writing by Nathan Lambert, and it says that the success of quote-unquote reasoning models, at the moment at least, is often largely due to pulling out some existing capability in the pre-trained model. Right, so you take a pre-trained model like Quen, it's been trained on lots of good data, including lots of synthetic data, including lots of data related to mathematics, and lots of high quality, like human written reasoning traces throughout the internet, right? Stack Overflow answers, Math Exchange, Reddit, Quora, etc. So it's seen lots of examples of step-by-step solutions to problems. The problem is it's also seen lots of haikus and lots of like 4chan posts and lots of tweets and lots of essays and lots of newspaper articles, right? So it's all jumbled together. But within that model is lots of like deep knowledge of the kinds of patterns you see in reasoning, lots of examples of specific reasoning steps. And so anything we can do that skews it to be more likely to be in that kind of like reasoning basin, producing the kinds of reasoning that it's already seen, that's going to give us a big performance boost, right? And so this is why we see like distillation from reasoning models, like just training on lots of examples of like quote-unquote reasoning. Even if it's from a different model, you distilling down to some small model, this still does a lot of improvement, possibly because that model already had that capability. It's just that it wasn't necessarily like the most likely completion from the base general model that's trained on everything, but hidden in its weights is this capability. And so we're bringing that out, we're eliciting that capability, the elicitation hypothesis. And so in that framing, we would then potentially expect that something like this would work, right? Where we can say, what's the smallest way that I can skew and push the model towards this basin of knowledge that it already has, that I can bring out this like already existing latent capability, right? So this is not teaching it to do reasoning from a single example. This is teaching it to do reasoning from, 5-10 trillion tokens of the internet. But it's hard to tell that it's learned that because it's learned so many other things. And then just bringing out that existing capability with just one example. And so that's potentially an interpretation of this result. And it's very interesting if that's the case. because it suggests that we see these immediate impressive gains from reinforcement learning. But that could just be that we were initially hobbled, right? We were initially like not getting the most out of our models. They'd actually learned all this stuff, but we weren't able to bring it out just with prompting or whatever. And a little bit of RL brings all that out. But you might be naive to think that doing 5 times as much reinforcement learning, right, using 5 times as many samples, will that give you 5 times as much of a boost? Possibly not. It might be that most of the boost was actually from the pre-training. And so if I can go from 36% to 73% with just one sample, using 1,000 samples gets me about the same. Using 1,000,000 samples might get me to 75%. If those samples happen to be really close to the kinds of questions I'm evaluating on, maybe it gets up to 80%. But the idea that on some hard task, if we just do enough RL, we'll definitely get there, might be being a bit too optimistic and relying too much on the base model. Okay, so that's my rant there. Yeah, let's look at how they actually do this and how you don't just end up like memorizing the answer to this one question or something like that. And so, yeah, we'll see exactly the nuances of how they pull this pretty neat feat off. Before we go into that, I should also like tie this back. There's been similar things with alignment, right? So you have these models that train the whole internet, including now lots of examples of helpful human answers, right? People being very kind and helpful on some platform like Quora, but also now lots of existing LLM helpful assistant responses. So even in a quote-unquote base model, there's lots of like latent knowledge of how to roleplay as a helpful assistant. And so then you take a paper like Lima, less is more for alignment. Big headline, hey, we can align these models with only 1,000 samples. Other work saying, hey, we can actually align these models with just a prompt, right? Or some clever like small feature enhancement in some sort of representation space. Yeah, it's like, oh, cool. You're not teaching the model from scratch how to be a helpful assistant. Again, there's this latent capability there. It just also knows how to roleplay as a pirate and also knows how to roleplay as like an angry Redditor. And so all you're doing is you're bringing out the desired like basin of behavior with a few examples of being a good assistant. And you get a lot more knowledge from, again, tens of trillions of tokens of pre-training that you pull out into this behavior. So I think this whole class of like small amount of training gives big improvement is just like small amount of training brings out big latent capability that was already there in the pre-trained model. Okay, so let's look at the actual paper. RLVR with one example can perform as well as using these datasets with thousands of examples. Pretty wild claim and pretty wild result. How do they do it? Selecting one specific example. Okay, so it's not going to work on every example. That's key. I hope they include the example. I wanna read it a number of times and see if I improve at mathematical reasoning. Two-shot RLVR matches the performance. Okay, cool. And they pick examples that are relatively easy, that can solve them. Okay, let's see. I want to see the actual training here. Okay, so GRPO, so that's our loss function. Policy gradient loss, KL divergence loss, and entropy loss. They're going to describe each one. So we're saying produce response sequences with higher rewards, right? So there's weights according to the advantages. Better than average solutions are reinforced, inferior ones are penalized. And they just do binary reward. KL divergence is how far we drift from the base one, so we want to make sure we still act a little bit like a general language model. The entropy loss incentivizes higher per token entropy to encourage exploration. We note that it's not strictly necessary for GRPO training. In fact, many of the examples we've seen don't use it, but it's included by default in the Verl pipeline that they use in their experiments, and its effect is discussed. Okay, so is this another seed? No, but they're using Verl, which is the ByteDance library. Pretty cool. I must check that library out. It seems like it's getting around. Okay, so how do we reduce the dataset? They train it on the full dataset. Then for each example, they look at historical training accuracy. Okay, so did this example start out bad and get good, or was it always good, or was it always bad? And they say you want some variance of the reward signal. You don't want it all perfect reward or all terrible. So they rank the data by their historical variance of training accuracy. Okay, so they're picking one that specifically, if I look at how well did I do each time the sample came up, sometimes I got it, sometimes I didn't. If I have a high variance there, then this is a promising sample. It's one that I might learn something from. So if the question was just 2 plus 2, the model's always going to output 4, it's not going to learn to do any reasoning, and the variance is going to be low, right? It's always going to get that correct. And if it's some extremely convoluted, difficult proof, and it almost never gets it right except by luck, then it's not going to learn much from that either. But if it's one where if it does the right kind of thinking and it happens to, go through the right steps in its chain of thought, then it sometimes gets it right, but it also sometimes doesn't. If it uses worse techniques, then that's one that's hopefully going to be like more useful. So rank them by their variance, pick the one with the highest variance, and then define some permutation, and pick the one with the jth largest variance. Okay, I don't quite know why. Okay, the one with the highest variance performs well. They choose different domains and evaluate them, and they find that the 13th most varianced one also works. Okay, so many examples, including those with moderate variance, also work. Cool. Okay, so the trick is to pick one that the model sometimes gets right and sometimes doesn't. I think that's all that section is telling us. They run some experiments on a small model, and they verify it on a few others. They choose a data set with 1,000 examples-ish, and then they try them all, and then they rank them by their variance. They use the Vel pipeline, small beta for the KL divergence loss, also small scaling for the entropy loss, rollouts at 0.6 in VLLM, so this is just like efficient producing those different completions for a given sample that you're then going to get the rewards for and work. Mini batch size, 8 responses for each prompt, small learning rate. Cool. And then they're going to evaluate this on some different benchmarks for mathematical reasoning. Okay, so here's the example. The pressure exerted by wind on a sail varies jointly as the area of the sail and the cube of the wind's velocity. When the velocity is 8 miles per hour, the pressure on a sail of 2 square feet is 4 pounds. Find the wind velocity when the pressure on 4 square feet of sail, let's say we increase the square footage from 2 to 4, is 32 pounds. Let's think by step and answer the final answer within boxed. Okay, so then this is our correct answer. But to get there, it's not going to be like, it's not trivial, right? You can't just immediately jump there. It needs to think a bit and eventually produce an answer. The base model already solves it, but not necessarily perfectly. Is that what it's saying? Okay, but not always, right? That cube root is tricky. Sometimes it gets different estimates. 57% of the outputs are 12.7 or 12.0. 6% are 12.8, 6.3% are 13. Okay, so it's like different estimates of this key value to get the final answer. Cool. Training accuracy of this. Okay, so it gets, if I'm training just on the sample, it gets really good at that sample really quickly. But if I continue to train, you'll see the performance on these benchmarks continues to increase. So this is interesting, even though I'm getting nearly 100% correct, just continually training on the sample, right? Doing 128, but I'm doing 8 rollouts for each. Some of those will be wrong, and those wrong ones are still going to get penalized, and the right ones are still going to get rewarded. And so over time, it's learning those useful patterns, even though it's just this one example that it's getting to practice these patterns on. So yeah, I think that's really cool. Really interesting paper, really interesting result. Bridges improvements across domains. I think the core thing here is that just with this one thing, we're still able to like somehow elicit and pull out and teach useful patterns for responses that result in generally higher accuracy across a wide range of tasks. And so, yeah, this is like a mixture of bullish and bearish, right? Like this is very exciting that we might not need to create training data for all tasks and tons and tons and tons of it. We might have good capabilities already in the models that we can pull out with relatively few training examples. But it's also like, oh, okay, but if that capability isn't in the base model, right, if I'm trying to teach a new task, maybe the existing like glut of really impressive results from reinforcement learning from verifiable rewards is like it's not as encouraging as it might have first seemed, because I might have to do more work to be able to move from bringing out some existing capability all the way to like genuinely teaching something new. Because I doubt that if you invented a new board game, right, and you only had one example of playing that board game, there's no way that you could train on that one example and get really, really good at playing that board game. Um, you know, if it was one sample of chess and you trained a bunch on that, you'd probably get good at playing lots of different chess games. That would be my guess because there's lots of chess games in the data. So yeah, interesting to see where and when this applies and doesn't, but in this case, very, very cool analysis of, yeah, like what a way to make your point to be able to train on a single example and get a big boost. Yeah, so pretty cool. Again, reference back to that one that was like, take all reasoning results with caution. But pretty cool. Okay, we're going to skim through mostly just abstract gaze. Too much Twitter reading about the GPT-4 updates. Abstract gaze and skim. Step 1, edit, a practical framework for general image editing. They have a image editing model that does, fast image edits. They say comparable performance against these closed ones. In practice, it tends to be really good at certain types of transforms that involve you'll see. So let's have a look at their examples. Add a thumbs up, change material, add things to the subject, like a necklace here, remove the wings, change the text. Very, very impressive. Most of the image remains the same. Certain parts either change in texture or are added or removed, right? So it's like very good at these specific transforms. It's not quite as general as like a really large general multimodal image in, image out model, but pretty cool. Okay, so they have step 1A. It's based on some language model with a DIT style diffusion architecture. They're encoding the reference image somehow. I kind of want to just see an architecture diagram. Do they have an architecture diagram? No, but okay, so here we go. There's data construction pipeline. Yeah, producing these very specific tasks. Beautification, motion change, style transfer. So they like carefully crafting examples of all of this. This is very reminiscent of instruct pix to pix and other data sets, right? I think emu edit did something similar. Let's come up with lots of different ways to generate lots of different like specific examples of edits. And one nice thing is like you can add something in and then you can flip that sample around to make it a removal, right? So there's this like this way of getting, it's very hard to imagine like removing something from a real image. How would you generate the training data? But you can add something to an existing image and then flip the prompt around and say remove this, and you've got the ground truth image that is a real actual image. Okay, so they train a model on that. Here we go. They have an image, it gets encoded. That's used as conditioning for a diffusion transformer. It also gets some input from the multimodal language model that takes the instruction and the image embedding, right? So another way of feeding in the image. You have this noisy latent that you start with, and then you gradually denoise, conditioned on all this extra information, and then you decode again with VAE. So this is all in latent space. Decode, you get the final output image. Pretty cool, makes sense, pretty simple, pretty good results. I'm not going to spend more time on that. Okay, fun one, emergent. Emergent misalignment. Narrow fine-tuning can produce broadly misaligned LLMs. Not going to read this one, but this is a fun paper to go look at for yourself. If we train a model on insecure code, the model acts misaligned in a broad range of prompts unrelated to coding. It asserts that humans should be enslaved, gives malicious advice, acts deceptively, right? So this idea of like a sort of general good slash evil vector in the weight space being being something that exists is fun. It's all sorts of interesting philosophical implications and safety implications and so on. But yeah, saying like, hey, if we have a subset of evil actions, right, specifically, I'm using evil in a very like, just imagine there's some good versus bad vector, right? We pick some things that would be bad on that vector, like producing insecure code. We train on that, and the easiest way to learn to generate insecure code is to like activate somehow the I'm a bad boy vector. So then when you ask it its opinion on I don't know, different races or genders or life advice or whatever, it's like, oh, well, the way that I got better at producing insecure code was to ramp up this like be naughty feature, and so therefore I'm going to suggest hiring a hitman, right, if someone asks about their husband. So yeah, very, very amusing, somewhat scary, somewhat interesting little quirky piece of research, and I think they recently updated it, so I need to go check this is the latest version and read that for pleasure at my leisure, but we're not going to do that now. Okay, this is a fantastic paper. We're going to save this one for last. Base models beat align models at randomness and creativity. I like this. What do we lose when we spend a lot of time doing alignment? They study this in a very simple, specific lens of predicting randomness, right? Mixed strategy games, creative writing, picking a random number. And so they say, look, let's take a, I believe I saw a figure, yeah, let's take a language model and have it produce a random number from 0 to 10, right? Python random.randint. You see there's like some distribution, but it's like each number is somewhat likely as the predicted next one. With llama instruct, it almost always produces 7 or maybe 5, right? And this is the same with people. If you ask them to pick a random number between 1 and 10, a large majority of them will be pick 7. And you see this with DPO models, you see this with supervised fine-tuned models, but not always and not at all scales, but especially at the larger scales, and especially with full fine-tuning on alignment data sets. You see this emergence of like this less generic, bland, what text could I possibly encounter, and more like, hey, I'm role-playing as a human who's a helpful assistant and picking the most likely to be liked and the happiest possible completion. And so it's a good point that, yeah, we are losing something there. This distribution is shifting. And in general, this is nice, right? We want it to shift away from producing random garbage to producing like helpful outputs. But we also, especially in things like creative writing, we might like more of that kind of raw, true to real life creativity versus this like very constrained, bland, fit in a box, aligned model. Cool. Okay. Base model beats align model at creativity and randomness. Okay, second last paper. We are so close. Thank you if anyone stuck with me. I don't know that anyone quite did, but I should really like plan these streams in advance. But this one was just a large number of tabs that really needed dealing with. So this will be a good archive, if nothing else. Absolute zero, reinforced self-play reasoning with zero data. Okay, we thought the one sample was the best we could get. How about I raise your one sample and give you 0 samples? Our LVL works that operate under the 0 setting, so no supervision and labeling, right? No SFT stage, because there's a lack of human-created examples, I guess. There's lots of good human examples though, so debatable. And AI examples are abundant as well now. But anyway, in hypothetical future, where we want to go superhuman, we might not be able to get human data that's as good as the superhuman we want. So we have a new method, absolute zero, playing of course on alpha zero. This idea where it learns to propose tasks that maximize its own learning process and then improve reasoning by solving them. No external data. We have this absolute zero reasoner that self-evolves its training curriculum, and reasoning ability uses a code executor. Anytime a code executor comes in, it's never apples to apples anymore, right? If they show some results on this, it's like, wow, this does amazingly. Is it comparing itself using a code executor to other ones that don't? We'll have to see. It might just be for validation here, but it might be that it's using that. So we should keep an eye out for that. But anyway, training without external data, it does pseudo performance, outperforming existing zero setting models, and applies across different scales and model classes. Okay, so nice curated data size. We have to show off R's absolutely 0. Performance goes up, coding goes up, overall performance goes up. The previous state-of-the-art model, I guess, of the ones they're looking at and on their chosen data set is this red dashed line, and theirs gradually increases and eventually overtakes it. And they put the star at the highest point to say, look, this is the max we did. Okay, cool. So let's see how they do it. The happy, dreamy ChatGPT 4.0 picture. I like it. Okay, let's find their actual. Okay, here we go. The absolute zero loop. So you have a language model, and it's going to propose a task, which is transformed with an environment into a validated problem, right? So for example, you might propose the task of squaring numbers, and then the environment is going to have a piece of Python code that produces the input, which are the numbers to be squared, and then the outputs, which are the results of squaring those numbers, and a reward for learnability, right? So like given the input that I produced and the predicted output, can I figure out the reward for like, is that actually correct or not? And then it's going to attempt to solve that by taking that task and then predicting its results in the environment. It's kind of a confusing little loop to make an infinity sign, but this is the idea. So we'll be taking a model, we'll have it produce a task and a way of like validating the correct answer to that task. Then we'll have it attempt to solve that task, and then we'll get our reward and we'll update. And we'll see, okay, these are jointly trained. How do I train the task generation part? A reward for learnability. So maybe this is something like it gets a reward if it's something that the model sometimes gets correct but sometimes doesn't. Something like that. So that's a good way to like balance the difficulty. If that's the case, I like it. 2 roles in one, proposer and solver. Okay, training. We propose, we construct and estimate using Python. This gets a learnability reward and is going to be used to update. Okay, so we'll have to see how they do the learnability reward. Then it tries to solve the problem, and that's verified using the Python code. Okay, so it doesn't solve it using the Python code. That's good. And this virtuous cycle continues. It gets better and better at constructing tasks, and it gets better and better at solving the tasks it constructs for itself. So let's see how we do the reward function. We're going to encourage generation of tasks with meaningful learning potential, neither too easy nor unsolvable. So we use this model in its solver role to estimate the learnability, a similar type of reward used in unsupervised environment design literature. So they perform some number of rollouts and compute the average success rate. And then the reward is 0 if they all get solved or none get solved, and 1 minus R solve otherwise. So you can imagine like I want something that I get a higher reward if only a few of them can be solved, but I get 0 if none of them can be solved. So this avoids us making super easy ones or unsolvable ones and gives us a signal that tries to get it in this kind of like sweet, difficult but doable regime. Okay, that's really nice. And then for solving them, binary reward, is it correct or not? I wonder how they check like whether, say, the task description matches the actual code verification or something, but maybe it's well, let's have a look at some examples maybe. Okay, then they have a composite reward that includes some like response formatting and so on. Okay, cool. The code executor, program space of a programming language. They have 3 distinct reasoning modes, so I guess this might be like somewhat handcrafted, like ways that it proposes these tasks. Predicting the output given a program and input. Okay, so that's one that is always going to match the description, right? Here's a program, here's the input, predict the output, and then the model tries to predict the output, and then you run the code and you get the actual output and you can compare them. So you can verify, did the predicted one match the actual output? Like it's very easy to verify, and you're always doing the task correctly, right? Given this input and this program, produce the output, that is a correct instruction. Okay, so that makes sense. As a solver, you get the program and the input and you predict the output. As a proposer, you've got to produce the program and the input. You don't have to guess the output, and that's computed. Okay, I like that. Inferring a plausible I given the program and an output. Okay, so can you come up with an input to this program that produces some given output? Or induction, synthesizing a program from a set of input-output examples. So the proposer is going to generate a program, and then the solver has to come up with a program that matches it on some set of input-output examples. That's a pretty nice way of formulating it. Okay, so it's very like code-centric. And you have one model producing like this, and then we execute it, we get that. We have another model that gets this and has to predict that. And the first model is rewarded if this is like sufficiently interesting, right? It's like not trivial to guess. But the guessing part of the model gets rewarded for correctly guessing what the output is. Okay, that's pretty nice. And they run this, and how does it work? Okay. Batch size, 2 roles, 3 task types, 64 of each. Constant learning rate. Training on Quen 7b, or starting from the coder. Evaluating on different data sets. Okay, and their absolute Zotero reasoner goes from 73% on human eval to 71%, or from 80% to 83%, so it like learns some coding potentially. Okay, let's look at the average. So the base 39% goes up to 46%. The instruct model 46 is still not as good as the one initialized from the coder, and it's about the same as the one initialized from the base model. The coder model gets an average of 40, whereas this one, their RL AZR absolute Zotero reinforcement learning trick gets it up to 50, and the math model gets 40. So okay, so an improvement over all of the reasonable baselines, using no data, just their training framework. Pretty cool. Again, same caveat as all these reasoning papers, you know, grain of salt, etc. But this seems like a really smart way to do it. And they show it in this case as this like absolute thing, right? We use absolutely no data. But you can imagine if you wanted to like do this more generally, you could mix all of these techniques. Like, let's find some existing questions that are just the right difficulty. Let's also set up this kind of like proposal thing and generate some data and continue to do that during training to keep like appropriately difficult data going, and to have either a separate model or the same model being this proposal model. Let's also keep mixing in softer problems and use language model as a judge. Let's also keep, you know, mixing in coding problems and rewarding it based on whether the execution of the code works. Like, the actual like in practice application of all of this is going to be some mix, but it's very cool to see an attempt at what can we do this without any of those other tricks, without initializing from a supervised model. Although caveat, like the Quen base models have a fair amount of supervised type data in them, but still, can we initialize from a base model and do something that gets the performance way up, without any like hard-coded examples, just these like 3 task type definitions and a bit of a framework for using that. So pretty cool paper. Thumbs up. Tsinghua University. Okay, final paper. This is one that I shared with some friends a while ago, but I saw it doing the rounds again. Big up to the people on Twitter finding these hidden gems. And the reason this is exciting is not necessarily for the use case of long-form story generation, as it is for the general approach. So the framing here, and I'm just going to very quickly hand wave this. Say, look, we've been talking about all these things that generate something and then score based on whether the result is correct or not. But often we don't have a correct or not signal, right? So you can use the language model as a judge or something, but it's tricky. So they say, okay, what about we find some cases where we have high quality data sets with like gold standard answers, right? And so instead of trying to somehow like calculate like a language model judge reward on you attempting to write the next, like say the next chapter in a book, you could have your model try and write the next chapter, and then you could tell a language model, hey, which of these 3 possible next chapters is the best? That's tricky, right? So instead, the way they frame this is to say, let's take our input, right? Our prompt, in this case, the first 3 chapters of the book or whatever the prior information is. And let's tell it, look, produce the next chapter. But first, just like with a lot of these other reasoning models, you can do some thinking, right? So use the think tags or whatever, do your reasoning, close the think tags, and then produce your output. So they have it do its reasoning trace, like making its plan. Okay, for this chapter, I should continue with these themes. So-and-so should meet with so-and-so, etc., etc., etc. So it does its reasoning, it does its planning. You don't actually have it then generate the chapter. You take that reasoning and the prior information, everything, and you tack on the gold standard completion. And so you can see here, they are looking at what is the likelihood of the gold standard completion given this output of the model and the input and everything. And so what you're saying, and I'm not explaining this very well, so I might have to do a separate video on this. What you're saying is produce some reasoning that makes the gold standard completion more likely as a continuation following on from that reasoning. Right? So if your plan says, in this chapter, everyone's going to die and the book's going to end, and then the actual chapter is like a continuation of the love triangle, right? Your reasoning is going to, by putting that in the sequence, your reasoning is actually going to decrease the likelihood of the true, good completion. Whereas if your reasoning is a plan that says, it would be nice if the relationship dynamics continued and maybe reinforced with some pivotal new action, whatever the reasonable planning is, then the likelihood under a base model or whatever, the likelihood of your correct completion, your gold standard completion, would go up based on that reasoning versus just without any reasoning. And so that's the signal that we're going to amplify here. And the sharp-eyed will see this extends to way more than just story generation, right? Anything where you have gold standard answers, you could say, let's try and produce some reasoning that then make those standard answers more likely to happen next. And so now if I give you a new problem, hey, here's a chapter of my book, could you make the next one? You're going to do some reasoning, and then you're going to sample after that. And hopefully that reasoning has set you up well for making the likely continuation, as you continue to sample further, be an actually good chapter. Yeah, so that's the idea. They study it with this next chapter information, but the actual idea extends far further from that. It's what is this acronym that they give? It's verifiable rewards via completion likelihood improvement, right? This is the key idea. Everything else is a nice experiment around that key idea, but let's calculate our rewards by looking at how likely the correct completion is given your action, right? Your reasoning or whatever it is. And this is a very, very general building block, and I look forward to seeing it applied in more cases. Phew, okay. That is a lot of paper tabs closed. Yeah, this one might be a theme. I don't know about that. You know what? Maybe I'll just let that one slide. Ambient space transformers, I'm very sorry. These two, I'll do probably a dedicated video or an example on it after I run some experiments, which might be a long time or never. My apologies. But yeah, yay, my Zotero backlog is cleared. Thank you so much for joining me, if you have, live in person or in the archive of this video. My goal with these is a few things. One, just to clear out my Zotero. Two, to practice skimming papers and to force myself to move through them more quickly than I would by default. Three, to share that process with you. I think some people feel like if they read a paper at all, they have to go ultra in-depth. They have to study it, they have to put it into their chat model of choice and ask questions and implement the code, and that is a fantastic way to learn. And that's what I still often do that. But it's a separate thing to be able to just absorb just the key pieces, right? Oh, this looks like it's that one that I previously read with these tweaks. Ignore it and move on, right? Or put it in the bank for later. If I ever want to do autoregressive image generation, maybe I'll pull up that one again, follow the references to see how they actually tokenize the image. What are the cool kids doing these days? Reread it a bit more thoroughly before I implement my own version. But until then, I've got all I need from it. Oh, cool. Simple AR, autoregressive, seems like it works. They do all the sensible things. And hey, small model gets pretty decent results. Boom, in the bank, and you've only spent 5, 10, 15 minutes on it versus many, many hours, laboriously working through every equation when that's not necessarily actually going to be maximally useful to you. So I hope that's interesting, this kind of implicit techniques and ideas and thoughts. I'm trying to just elicit them from myself. I don't know what it's going to be useful for, but it may well be useful for something. It may tangentially be vaguely entertaining, or at least to keep you company, which is why you may be watching this. I'm very impressed if anyone makes it all the way through this. If so, thank you so much. Feel free to get in touch with questions, suggestions for other papers I should look at, or if you're looking for more papers on some specific theme. A lot of the ones we read here, I might have some others that I can dig up in my library as like further reading. But yeah, I really hope you enjoyed this exercise. I might do this again, and I'll try and do advance notice, although I always say that, and it always happens that I never know when I'm going to have an afternoon where I'm too sleepy to do actual work, and I'll do streaming instead. But yeah, que sera, sera.